Okay, so we'll continue with ratio estimation and then move on to regression estimation. So previously we focused on bias and ratio bias. Uh, and now we're going to move on to variance. So for usually for variance, to compute the variance is enough to have a first order Taylor expansion. But here I intentionally did second order Taylor expansion to just to show you how to do it. So let me we'll lead this technique later. Maybe sometime. Should be okay. So let me write it. Ratio x y hat for the Thompson divided by x hat, right? So this is the ratio. So what you can do is to use okay. So if you sorry, should write it as a 1 plus delta. So if you write this way, then delta is what? Delta is x hat minus x. Right? It's just algebra. So supposed to be true. And then we have a nice cancellation. And then what you can see, I mean, this is kind of my technique without really deriving the differentiation. First order differentiation, second order, right? If you want to do a second order Taylor expansion, you need to evaluate the first order, I mean, the differentiation, second order differentiation. If you want to do third order Taylor expansion, then you need, there will be quite a lot. But here's some technique that I kind of like to very much, is that you can actually, you have only to worry about the Taylor expansion of the second term, which is actually what? Right? So this is actually that's the job of doing Taylor expansion. So this is true, right? And this is, algebraically true. So that means whatever you obtain from the Taylor expansion should be equivalent logically, right? You cannot get the two different answer, right? So that means this should be equal to your Taylor expansion. So end of the day, you can see that this is what? X over y hat, x hat minus x plus another way. So, okay, sorry, I should have, maybe it's probably better to write the first term too. Something like y plus, because I want to make sure that we have a first order term, second order term, something like that. Okay, so I now have a expansion. So this is kind of a second order expansion. So you can see that this is the constant term is this one. And then first term is what? First term is y hat minus y minus x over y times x minus x, right? And then second term is should be, so how to compute the second order term? This is second order, this is first order, first order. So first order times first order, you will get second order, and second order times constant, you will get another second order. So that means your answer will be y over y times x hat minus x over x square, and then minus x 1 over x hat minus x y hat minus y. Okay, so that is the Taylor expansion. Second order Taylor expansion. So you have a constant term, first order term, and second. Okay, so that is the basically this result. Right? Yeah, should be the same. So that's the derivation of this. Okay, and then notice that this is what is the expected the order of this one. So basically, when you do this kind of Taylor expansion, the idea is this guy is 1 over root 10. I mean the rotation. I haven't really introduced this rotation, but another way is so this is bounded improbability. So main message is that you can so this is the mean estimator, right? Okay, sorry, should have a bar. So as a estimator for the population mean, this guy will have a variance 1 over n order. So this is basically this estimator is unbiased to 0 and variance equal to 1 over n order. Then you get this result. So to be rigorous, let me briefly explain. This is probably beyond the 521. Okay, but how to? But I will just so what is the exact meaning of this one? Bounded improbability. So the definition of this one is that we can actually have something like so given epsilon, we can find m such that this probability statement is true. So you can, no matter how small your epsilon, you can basically find the big enough n such that the probability, so the probability that outside, right, can be negligible. So if you have a much smaller epsilon, then you can make it wider, right, bigger and bigger, something like that. So so to prove this, and prove is that you can actually uses Chebyshev inequality. Oops. Oh, sorry. Not epsilon. This is M. So that means you have a M epsilon. So we want to make this one to be less than epsilon. So this is first the numerator is a kind of bounded, right? Because this is a variance. So you have a certain variance. This is a variance, but n squared. So if variance is 1 over n order, then this will be bounded. So the given epsilon, you can choose m large enough to make this happen, right? So that is the basically the idea. But this is actually 621 level contents. Okay. So our point is this guy or 1 over root 12. So it goes to 0, but with the rate of the 1 over root 12 order. But here, the square term, this is 1 over root 12. This is 1 over root 12. So product of these two is actually is 1 over n. So the first of the term goes to 0 in the rate of 1 over root 12. But second of the term goes to 0 in the order of 1 over n. So it goes to 0 faster. The second order term goes to 0 faster than the first order term. Okay. So in that sense, the second order term is negligible compared to the first order. So that's why we want, that's why so to rigorously, we have additionally the second order term, right? Second order. But this guy is 1 over n order. This guy is actually 1 over n squared. So this is a smaller. Second term is smaller than first. So asymptotically, we don't have to worry about the second order. This one dominate in the asymptotic sense. And also you can see that this one, I think we covered this before, but this guy and this guy cancels to each other, right? Y bar minus r times x bar is equal to 0. So you don't have to worry about this constant. And so then the first term only has this one. So basically, so my point is here, this guy, right? This guy is the first order term, but then you can see that this is hat, y hat minus r x hat, because this will cancel to each other. So that is summation over a 1 over pi I yi minus rxi. So you can write it as a kind of Hermite-Thompson estimator over the residue. I mean, residue over the ratio prediction. So then we can call this as EI. Then if you call this EI, then this is nothing but a permittancy estimator of total of EI. So that basically justifies this result. So let me that basically justifies this result. The ratio estimator can be approximate the variance of the ratio estimator can be approximated by the variance of the this third permutation estimator, where this EI is the subset by the yi minus r times xi. Okay. So now the another question you can think of is when the ratio estimator is better than the permutation estimator. Not always. Sometimes it could be worse, but and then let's see. So because we have these approximations, right? Because we have this approximation already, you can expand it. Then you get this. And then you can write some inequality, right? This is what you are interested in. When the rate variance of the ratio estimator is smaller than the variance of permutation. So this one is equivalent to having, as long as this one is negative, right? As long as this term is negative, then you are it's equivalent. So then you can express this inequality to get this, which leads to this relationship. So the correlation is quite high, right? Then most of the cases you will be okay. The ratio is made, but will be efficient. So let's try to understand what is going on, right? What do you mean by this? So this is a little bit general. So let's if you write it as a I mean simple random sampling. So on the simple random sampling. Then this is just the correlation of x and y, random variable x and y. And then you have something like so end of the day you have as x square. This is sy, so actually no square. Right? So if one interesting part is that so this is relatively speaking, if y is really small. So let me see. As x is small, then we will have this inequality very likely, right? Because the this is close to zero, then this will be goes to zero. This will goes to zero. Then that means yes. Then ratio estimator is good. Is good. But another interesting part is that if X bar, population mean of X is close to 0, then that means what? That means the right side is likely to be high. So maybe it's not like this inequality may not hold, right? So then the ratio estimator is not good. Which makes sense because if you think about the ratio estimator, right? So on the simple random sampling, this is the population mean of X and the sample mean of X and then Y bar, something like that. So if this is population mean of X is close to 0, that means what? The denominator of your ratio estimator will be very close to be 0, right? So it's almost always if you have something very small in your denominator, it will create a lot of variation, right? So it's not really a good idea to use that X to apply ratio estimation because you will actually make it worse, right? Then in that case, it's better just to use the Hurwitz-Thompson estimator than the ratio estimator because the denominator, so the fact that mean is close to 0 for auxiliary variable is not really good, especially in the ratio estimation. So that is something I like to emphasize. And then let's move on. And then variance estimation, because this is so variance estimation, because we already have this variance formula. But the only thing is that we unknown is this is unknown, right? So we cannot really compute. So now question is how to estimate it. So we have two steps. First, this is actually what? This is you can see that this is S E squared, right? So this is a population level S squared. So we need to use the sample level S squared and then plug in EI by EI hat. So we need to estimate it from the sample. So then this is our estimate. That is the classical variance estimator. But actually there's an alternative method. So alternative variance estimator is that we first recognize this relationship, right? So because R hat is a X times R hat. I mean, the ratio estimator is X times R hat. And this is constant. It's not really random variable, right? So the randomness solely comes from the randomness of R hat. So why not estimate the variance of R hat first? So then this is your variance estimator, R hat. And then this guy is the same as before, right? This guy is exactly equal to this guy. This guy. So this is actually variance of what? Variance hat of Hurwitz-Thompson estimator. Right? So that means you actually multiply this guy. So this is you can call it, this is a method 1. This is method 2. Then this is a variance estimator of the method 1. On the method 1. Okay. And this is your variance estimator on the method 2. So your method 2 variance estimator is this times the variance estimator on the method 1. And then this guy is what? is actually you used in the ratio adjustment. Right? So then we know that this will converge to one approximately. So it will converge to one asymptotically, but it's not equal to one in a finite set. So we have that means we have two different choices for the variance system. Which one do you prefer? Method one, raise your hand. Method two. Okay. We have one preference from for method one. Method two. Okay. Well, this is not easy question. Actually, this is not something that you can answer right away on the spot. But so here's some hint. In many cases, right? So this is say X and Y. So really, if you think of the data using the ratio estimation, the basic idea is there must be some kind of a positive correlation, right? So this could be a crab acre. This is a crab yield, right? So maybe the leadership should be proportional, but also in terms of the variability, it's probably more like this, right? So the variation. So suppose small, right? Small farms will have some variation, but not really a lot, right? Because it's small. The scale is small anyway. But the big ones may have more variation. So in terms of that, this adjustment actually, so okay, this guy is just comparing the so not this guy is actually computing something like this. So this one has nothing to do with the X. So it just computed this variance, but the ratio of adjustment factor. So suppose this is a mean, right? X bar, and the right side, it actually what? So what is the ratio? Well, so idea is this in the left side that this adjustment factor will be more likely to small, and here the adjustment factor will be more likely to be large. I'm not sure how, I kind of forget why this happened. Anyone has an explanation? So I guess we have a randomness, right? I mean, so we are kind of doing average. Well, okay. I think about that. I will explain it next class.
Looks like this X bar divided by X hat is smaller when the overall sample is under, like, just underestimate, so.
Right.
Inflate variance into the middle, and on the other side.
That's right.
Reduce that.
Right. So yeah, right. So that's very, thank you. So yeah. So if this is a smaller, less than one, right? Smaller than one, we know that, right? We know that we happen to select a small samples, right? Small farms. But true variability will be large. It's better to, okay. In that sample, right? If my sample is mostly here, then my variance estimator will be small because the sample element will have a small variability. But and so we want to inflate. So it's actually inflating here, right? And on the same way, here, if you happen to select sample element in this part, then my estimated variance will be high, right? So because of the residual will be high, right? So my estimated variance will be high, but I know that the original sampling design should have on average in these places. So we should downweight. So that is the kind of idea. Yeah, thank you. Very good. So yeah, let's move on. Okay, let's move on. So now we're going to move on to regression estimator. So I'd like to emphasize that regression estimation is really important in survey sampling estimation. And Professor Fuller is a kind of a pioneer on this area. So I heard from his good friend Professor Rao that actually they were kind of a office mate when they were assistant professors at Iowa State University. So Professor Rao told me that at that time, people just happy with the ratio estimator. But somehow Fuller keep working on a regression estimator and develop the whole foundation. So anyway, so study variable, we have now we have a vector, right? Vector of auxiliary variables, study variable. And so we have this information available in advance. We still are interested in estimating the population total. And then our estimator can be different from the population total. Okay. So basic idea is something like this. You can think of this way, right? So you have an X observation throughout the population, Y information only in the sample. What should we do? Well, one idea is, okay, let's use the sample as a training data, training for your model prediction. So you learn the relationship from the sample data, and then use that to predict all the elements in the population, right? You can do that, right? So then you can create Y hat throughout the population, and then use that to estimate the population total. So that's very simple idea, but maybe there's two problems, right? Two questions, I'd say. Two questions. The first question is how to compute, right? Y hat, how to fit a model and learn from the data when you have a survey data. Second part is, what if my model is not really good, right? So this is a very natural questions. Okay, so when you want to compute the prediction, right? You should employ, you are thinking of some model. So the easiest model we can think of is a regression model, right? So this is a very, we may come up with a more complicated model later, but as a start, right? As a building block, you can start with a linear regression type model. And if you are not really comfortable with making an equal variance assumption, then you can actually assume that it increases with some function of x, right? So you can assume that Ci is known, but parameter beta and sigma square is unknown. So this is a superpopulation parameter. So we have a so finite population is regarded as a model, and then we call that model as a superpopulation model. And then this because we allow for unequal variance, the model is called the generalized regression model. So, and in short, correct model. Okay. And then the first question is how to estimate the model parameter beta. Well, you can. So we have a kind of two-phase idea. So first, think of what would be the parameter if I have a census. So what would be my estimator, right? But what if my sample happen to be census? So in that case, I know what to do, right? Because this is population is nothing but IID type sample. So that is my estimator. I mean equation. So estimating equation. I solve this one for beta to get beta hat, beta, and then to distinguish with the beta hat, we can call this beta n, subscript n, to emphasize that it's based on the census. Okay. And then the second step is that let's find out a Profit Thompson estimator for you. So here's basically you have this equation, but you estimate it from. So you have an estimating equation. So because the estimating equation is just the population summation of a certain quantity, right? So you can construct the Profit Thompson estimator for that function. So sometimes this in the literature, this is sometimes called estimating function. And the equation is called the estimating equation. And at least for estimating function, we can construct the Profit Thompson estimator by just changing the summation, population summation by sample summation, and then multiply 1/pi as the weight, right? And then idea is okay. The idea is okay. I know that this guy is estimating this guy, right? I know that this becomes an estimator of the estimating function. Census estimating function is estimating the population estimating function. So the solution to here, right? The solution to here may, so this is a kind of a, converge in probability. And then the solution, this is a solution to here. And then under some conditions, maybe this will converge. Okay. And so there's some theoretical, so it's not just the convergence here, it's actually uniform convergence. Uniform convergence in probability. So that kind of condition is needed to show, to justify the convergence of the solutions. But this is beyond the 521. Okay. So anyway, we are able to obtain our estimator from the set. So you can see that this beta hat is not so not exactly equal to this, but maybe approximately okay. Because this is a kind of nonlinear, right? So it's not really, so this guy, at least you can see that this guy, the new, I mean, this part will converge it to population summation of 1 over Ci, Xi, Yi. And this guy will converge it to, so in converge it to population level of the 1 over Ci, Xi, Xi prime. So in the limit, this beta hat will converge to the this guy inverse and this, right? Which is beta. So again, this is nothing but Ci inverse summation of Xi, Yi inverse Ci. So my point is that this guy is this guy, and this guy is this guy. So each component will converge. So maybe asymptotically the limit will have this. So so Craig estimator can be defined as a prediction estimator on the Craig model. So that is a simple. So I already discussed the estimation of beta, which is beta hat this form. So we can just compute the prediction and then take the total, right? And if Ci equal to 1, so equal variance, then you can call it a regression estimator. Another part is that ratio estimator is a special case of the Gray estimator using Ci equal to Xi. So Xi is a scalar. So if Xi is a scalar, then beta hat is what? Summation of pi I 1 over Ci Xi square, right? Inverse 1 over pi I 1 over Ci Xi Yi. And then Ci equal to Xi. Then we have actually cancellation. Right? So then this one is indeed become equal to R hat. So ratio estimator is actually a special case of a Craig estimator for the choice of this. So that means the theory here is very general, covers many estimators. So here is some for example with the regression estimator. So you can see, this is a little bit small, but we have a population. So we use a sample size 30. Okay, we use a sample size 30 from this model, from linear regression model, right? With x from normal to 2 and error from normal 0 1. Okay, and then we have a 30 point, basically 30 point. And what would this red line means? The red line here means population mean of X. Well, actually, we don't know the we don't, so you may, so, okay, well, it's true. So population mean of, but we don't have a finite population here. So then what do you mean by finite population? That is, N is infinity. So you can think, right? N is, which is actually means that mu X, which is 2. Because I have a normal from mean equal to 2, right? So this is 2. And sample size with a particular realization, I have a randomness. So my sample mean is 2.14. Okay, so my 2.14 is sample mean. And then in this particular sample, my sample mean of Y is 8.23. Okay. But what is the mean of Y, by the way? True mean of Y is 4 plus 2 times 2. Right? So that is 8. Because I use the this regression model. I know the truth. I know the true parameters. So I can compute the true mean, which is 8. So you can see the discrepancy, right? So truth is 8, but I get 8.23, and which contains a sampling error. Okay. And then this blue line, okay, this blue line is estimated regression coefficient. So linear regression, I use a sample size of 30 to fit a regression model. This is my regression. Then let me ask you one. What is, so this is a 2.14 X bar sample mean, right? So then if what is the prediction? But here, then this will be what? Sample mean of Y, right? Which is 8.23. Because of the property of the linear regression. Like this, your prediction at the sample mean will be the sample mean of Y, 8.23. But what is the prediction used at the truth? This is actually this one, right? You have a beta 0. So here, and you estimate, because I know that my sample has a bigger element, right? So because my sample mean is greater than the population mean, so I know that I should have maybe downweight a little bit to reduce my estimator. And how much is based on the regression relationship. So if I use that, the regression estimator shows 7.941. Okay. Well, you may say that, well, your regression estimator is also has error, right? It's not accurate. Of course, regression is, I'm not saying that regression estimator is perfect. What I'm saying is the regression estimator actually has a smaller error, right? Than the sample. So this one has a sampling error. Okay, so then maybe you may wonder how to improve the regression estimator. In other words, how to reduce this, right? So what if I use population mean? I mean, population linear relationship. So I know that this is truth is 4, truth is 2, right? So basically, the true beta true beta 0 is 4, and true beta 1 is 2. So if I use these numbers, right? If I know this, use these numbers, then my prediction will be exactly equal to 8. But I do have this, sampling errors because I compute the regression coefficient from the sample. So that's the price that we pay. But it's the sampling error at the end of the day is similar generally. So I will see more carefully using some theory. So, but hopefully this example can help you understand what's going on with the regression estimation. Okay. So first, so now let's investigate the properties. One of the property is, first property is mathematical property. I mean algebraic properties. So it first of all, it is linear in Y. So X regress greg is X prime, oh no, X bet. So yeah, 1 over N. Let me write it this way. Right? And then this guy is a linear in Y. Right? Beta hat is a linear in Y. So this one also will be linear in Y. Okay. And then if you write it as more specifically, this is actually summation over 1 over pi I Ci xi prime inverse 1 over pi I Ci xi yi. So I can just put everything into here and call it G, and Gi is this. And this Gi satisfies this property. Why? Because if I let me do some algebra. Pi I Gi right, inverse xi Ci inverse xi. Okay, so let's try to prove it. Okay, so showing you can either way fine. So let's prove the this version, and then this summation can go all the way to here. So you can actually have this one, and then summation over a 1 over pi I xi prime Ci. And so this guy and this, what is this guy? Is this guy, right? So they are actually the same. So they cancels. So you get this one. So that is purely method, algebra. And the meaning of the interpretation, right? Critical interpretation of this, identity is that if you use xi instead of yi to your regression estimator, you will obtain the population total of the xi. So it recovers the population total of x's from the sample. So that is a very important property, right? Calibration property or benchmarking property. So calibration or benchmarking. And then now we want to move on to statistical property. So first of all, we need to understand that it is like the ratio estimator. Ratio estimator is biased, right? Ratio estimator, biased estimator, but the bias is negligible. So we'll do the same. It's the same story for Gregg estimator. So Gregg estimator is biased, but the bias will be negligible in the end. Okay. So now how to check? So so this guy is xi prime. So yi hat is xi, that hat, right? Prime. So when you take the expectation is expectation beta hat. And then expected value of, so let's assume that let's kind of accept the fact that this one converges to beta n. So this guy is indeed close to beta n. Then this guy is equal to this guy. So we should to evaluate this term. This is, by the way, population level residual, right? Residual of the regression. But we have a CI. So it's not really clear when this is 0 or not. Okay. So we are interested in how to make this. So under what conditions this will be equal to 0? Because we already established asymptotic equivalence here. So what we want is that this guy is indeed equal to 0. Then we can kind of get bias approximately equal to 0. So so condition is this one actually. Ci is lambda. So what do you mean by that? Well, is means xi contains ci. So ci is a scalar, right? Scalar. Xi is a vector. So you have a vector, auxiliary variable, but one component of x contains ci. That's it, right? I mean, or you can, the linear combination of x's actually produces a ci the other way. The way is fine. But this guy, this condition is important because it will imply two things basically. One is that this is 0. So the answer is that ci is in the belongs to column of xi. Oops. Or ci is xi prime lambda. So so under this condition, our residual will be 0. Some of the residuals will be 0 in the population level. And also the residual will be 0 in the sample level. So in the Hurwitz-Thompson. So this is the a sample residual, right? Sample version residual. So this sample residual will be applied to Hurwitz-Thompson weight, will be 0. So basically, this condition implies two things. One is the sample version. First, another one is the population version. Okay. So let's prove it. So what is the definition of beta n? Beta n satisfies so that is essentially the defining equation, right? It's defining equation for beta n. Beta n satisfies this. Plus, we want to use Ci equal to Xi prime lambda n. Lambda. We need we want to use, right? Implies what? Implies okay. So that's what you want to show. First of all. And by the way, this is probably to be rigorous. We should clearly see that this is actually a vector equation, right? So zero should be zero vectors, vector of the zeros. So how to show from here to here using this, right? How to show this? Well, probably you are tempted to first apply transpose and then multiply by lambda. Okay. So if you transpose y, then you can use this. Then this guy becomes 1. Right? Xi prime lambda is equal to Ci. Ci divided by Ci is 1. Same story here. Beta hat is the same. So you have a 1 over pi I yi minus xi prime beta hat xi c divided by ci equal to 0. So this is the defining equation for beta hat. And then you have a assumption that you want to utilize, right? And then what you want to show is the sample version of the normal equation, which is residual property, which is, oops, maybe I should. So how to show this? Well, we use the exactly same step, right? In the population as in the population version. So you want to first transpose and then multiply lambda both sides. Then you can get equal to 1. Oh, no vector. This is just 1. That's it, right? So this itself is just the algebra, but it has a very interesting statistical interpretation, right? So the statistical interpretation is that, okay, so we basically proved the first two components, And now that this guy implies that this is 0, right? So originally the definition of the Gregg estimator is just a prediction estimator. But now you can actually add this 0 and then respec, right? To get this. So basically this guy is moves to here, this guy moves to here, this guy moves to here. So then you have a Hurwitz-Thompson estimator and you use the difference. So this is estimate 0, but a certain choice of a beta hat, you improve. So it's kind of doing some sort of a projection to 0, those augmentation space, but that's kind of alternative expression for now. Okay, well, so you probably have seen, some of you probably have seen this expression some other places in the CSS and working group seminar or something like that. This is pretty much very popular technique. And here's my wrap up concept, summarization of the concept. So basically the expression 4. So why we are adding this one, right? So what's the point of adding this one? Notice that this guy is actually minus of the bias, estimator of the bias. So bias is this guy. Bias is this guy. And then how to estimate it? So suppose you can, this is population total, right? Population total of residual. So you can apply Hurwitz-Thompson, right? You can apply Hurwitz-Thompson method to estimate it. Then, so let's write it this way. Bias hat is minus A 1 over pi I and residual. Yeah, I have something like that. Okay, even though the bias is 0, but let's. So, well, to be rigorous, bias is 0 only when this condition holds. CI is in the column of X. If this condition does not hold, we can still compute the bias from the sample, estimate the bias from the sample, and subtract from your prediction estimator. Okay. Then, whenever you have an estimator, if you can somehow estimate the bias of that estimator and subtract it, then you can always make a unbiased estimator. Why? So let's take a prediction. So let's ignore the subscript and bias hat y hat minus y, right? So this is an estimator, expectation of the estimator, bias corrected estimator minus the parameter that you are interested in. Then well, you can, in other words, you can maybe to make it more general. Let's write it set, okay? Minus set. And then bias set. It's 0. Right? This guy is biased. So you have a, you can, so your estimator can be biased. But if you can actually compute the unbiased estimator over the bias, then you can always make it unbiased by subtracting the bias term, right? So you know, given the any prediction estimate, we can always remove this bias as long as you can estimate the bias. Okay. Is it good news or bad news? Well, I don't know. Maybe good news, right? And so condition 3 means that condition 3, right? Condition 3 this one, or it's basically sufficient condition for this one is this one. So basically the relationship here means that bias correction term is 0. That means there's no need for external bias correction. It's automatically bias corrected. So the prediction estimator is already bias corrected as long as Ci equal to Xi prime lambda holds, right? So if my Ci, if basically if I can use the when I construct the regression estimator, I can use X to include my Ci and construct the regression estimator, then I'm good. And that means the residual is 0. So then bias correction term is 0. So then it is automatically bias corrected. So this property can also be called internally biased calibration. So you know you can. It's quite important to make a good name, right? It's kind of branding, right? So maybe IBC is probably better than bias corrected estimate. So that is a kind of a term that I like to I like this term because it's more clear and emphasize the concept. So if the IBC condition is not satisfied, then the prediction estimator is no longer asymptotically design unbiased. However, you can still. So point is, okay, this is 0 on the IBC. So if IBC is not, if IBC does not hold, then we know that this is not 0. That means we should include this one externally. Okay. So to make a bias corrected estimate. So then we have a variance estimation, but I think I will stop here and continue in next week. So that's all for today.